So I wanted to carry on with yesterday's lesson by talking about the last of the three individual gas laws. And so Gay-Lussac's law is the last one of the three. We've looked at Boyle, we looked at Charles' law. Now let's look at Gay-Lussac. He kept volume constant. So in other words, if we were to envision this, imagine that I had a container and it must have had some sort of a lid. So it's closed. So we're fixing the volume. So even though gas inside, gas particles, might, be able to expand if provided the space to do so, they aren't because the volume is fixed. So I think we know what would happen. Think about if you were to throw some sort of aerosol can into a campfire, then you would see that because that volume is fixed, the increase in temperature is going to cause the particles in that container to move faster and thereby collide against the sides of the container faster, creating high pressure. And so as the temperature is increasing, as my temperature is increasing, my pressure is also going to increase accordingly. There's a linear relation there. And so we say that there's a direct relationship. And so I think when you look at this equation, this formula here, to relate pressure and temperature, it will make sense. I have my pressure, P2 over P1 is equal to T2 over T1. So we see that our corresponding final pressure and temperature on the same side of the fraction as our corresponding initial pressure and temperature. So let's take a look at an example here. So in this example, I have a gas at STP that is heated to 298 Kelvin. What is the final pressure of the gas? So it seems to me, I'm going to look at this and recognize that what I'm looking for is P2. P2 is my unknown in this circumstance. So given that, I know that I'm looking to figure out what T1 is, what P1 is, as well as T2. So let's write out those givens. So T2 is given to me, that's easy, it's the 298, so I'm just going to write that in. So 298 Kelvin, and it's also a good reminder that in these gas law questions, we need to ensure that our temperature values are converted to the Kelvin unit. Now, I'm going to remind you about STP. So STP stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is 101.3 kilopascals. And so now I have all of my givens. I'm going to go ahead and write out my formula. So I know P2 over P1 is equal to T2 over T1. And of course, in this case, my unknown is my P2. So I'm going to move P1 over to the other side of the equation to isolate P2. So that gives me, oopsies, P2 is equal to T2 over T1 times P1. And so let's go ahead and sub in our values for that. I'm running out of a little bit of space here. Let me see if I can just kind of move this up. There we go. So P2 is equal to 298 Kelvin divided by 273 Kelvin. And then times that 101.3 standard pressure, kilopascals. All right, so I want to also think about the reasonableness of my answer in this case, which is that if I am taking something that's at STP and I'm heating it, that in reality, what I should see happen here is that I should see the pressure go up. So I'm expecting an answer that is higher than 101.3 kilopascals. Just, reason out the question, and that might indicate to you that you've made an error if your answer does not seem reasonable. And so right now I'm getting, let me see, I've got 1, 2, 3 sig figs in my answer. So my answer, I'm getting 110.57, yada yada. So I'm going to write that as 111 kilopascals. So at this point, the worksheet that I gave you yesterday should in its entirety be something that you can manage, and I'm going to strongly suggest that you use today's time to finish any questions on that worksheet that weren't completed yesterday. But I'm also going to continue on with a second lesson. All right, so the second lesson today, I'm going to start our note on combined gas law and finish it after tomorrow's quiz on percent composition, empirical formula, and molecular formula. So the individual gas laws are great if only 2 of the 3 variables of pressure, temperature, and volume are involved, but under a lot of circumstances, you're going to see all 3 of those variables changing potentially. And so we take the ideas from the individual gas laws and come up with an equation called the combined gas law that utilizes all 3 variables and accounts for possibly all of those variables changing. So so same ideas are going to hold here. We're going to ensure that that our temperature is in Kelvin, has been converted to Kelvin if given in degrees Celsius. And we're going to start by, in any question, writing out our givens that'll allow us to figure out what's going on. All right, so let's take a look at this first example here. So it says 225 milliliters of a gas is at 75 degrees Celsius and 1.0 atmospheres. The temperature is lowered to 20 degrees Celsius and the pressure is lowered to 1 atmosphere. What is the final volume of the gas? Okay, so often in problems, the last sentence tells you what you're looking for. In this case, that is the case. And so I'm going to quickly write out that we're looking for V2. That is our unknown. And so if that's our unknown, in an equation such as this, we can't have more than one unknown. So I have to be given information about all of the rest of the pieces of the puzzle here. So let's figure out what we know. So I can see that I have 225 milliliters of a gas, and it's describing an initial condition. So I'm going to write that out. So that is my initial volume of 225 milliliters. Now, at this point, people will say, well, do I need to convert that into liters? It's not in liters. And I would say to you, well, no, not necessarily, because V2 is what we're solving for. But we just need to know that if I'm using milliliters as my unit for measuring volume, then any outcome resulting from that for a volume is also going to be in units of milliliters. Okay, and so now I've plugged everything in. I'm going to go ahead and calculate it out in a second here, but let's take a look at our units. I've got kilopascals up top and the kilopascals on the bottom. I've got Kelvin and Kelvin, which cancel, and that leaves me with units of milliliters. So I didn't need to convert to liters at all. So I have I'm going to go ahead and keep the 151.95 as the original value in that conversion for pressure, times 225. Divided by 348 times 298 divided by 101.3, which I'm getting let me see, I have, looks like 3 sig figs in my answer, so 289 milliliters. All right, hopefully that was okay. So here's the second question that I would like you to try out. It says 25 milliliters of a gas at STP is compressed to a volume of 10 milliliters. What must the new temperature of the gas be if the pressure is increased by 25 kilopascals? So write that question down, give it a try, and when you are ready to resume, then carry on with the video. All right, so I've gone ahead and written out all of the givens in this question. There's a couple of things I want to point out. My initial volume and my final volume are both in milliliters, so there's no need to convert either of those into a different unit because the milliliters and the milliliters will cancel out. However, if they were in different units, then I would most certainly need to make sure that they match. Otherwise, liters and milliliters can't cancel out, for example. I've incorporated my STP values, but one thing I also wanted to point out was this business of increased by 25 kilopascals. That doesn't mean that P2 is 25. It means that I'm adding 25 to my existing pressure to give me a new total pressure. Okay, so not sure how that worked out for you. Now, I want to take a look at our equation. Notice that I've flipped the formula. I've inverted both the left and the right hand side. The reason I've done that is because that makes it easier to isolate my unknown in this case, which is T2. And also allows me, I can easily see that in order to isolate T2, both my P2 and my V2 are going to get moved upstairs, and I'm going to be multiplying by it on the other side of the formula of the equation. So T2 is going to be equal to T1 over P1V1 times, P2V2. And so all that's left is for me to sub in those values that I have, 273 Kelvin divided by my 101.3 kilopascals and my volume 1, which was 25 milliliters. My P2 was that 126.3 kilopascals multiplied by my 10. So, the sig figs in this aren't really super convenient. Let's see what we get, and we'll kind of adjust from there. The question doesn't ask for my temperature to be in degrees Celsius. It just says temperature. So in that case, I don't really need to do any extra work to get it in degrees Celsius, but if it did specify that, I would need to go ahead and do that. I'm going to just make sure that I get this right, 126.3 times 10. So I'm going to double check that. So 273 divided by 101.3 and 25 times 126.3 and then times 10. Ooh, that does not make sense. I'm going to go ahead and check that again. 273 divided by 101.3 divided by 25 times 126.3 times 10. Ooh, I guess so. So I am getting a value of 136 Kelvin, and I'm going to ignore sig figs for a second here. Let's make sense of this answer. So I've compressed the volume, and I know if the volume goes down, then the temperature should go down. So that's in line right here with my answer of my much lower temperature. I also know that I have increased the pressure, and increasing the pressure should, if I increase the pressure, then that should increase the temperature. But the reality is this 25 kilopascals doesn't really increase the pressure that much. So I'm going to say that my answer makes sense. So what I want you to look for on Google Classroom today is a second worksheet that will allow you to practice the combined gas law. And we'll be sure to discuss this and do some warm-up questions tomorrow in class. So save any questions for then.